this section we're going to deal with integrals involving algebraic fractions. This is going to be a primer for our more extensive work on fractions in a section called partial fractions, where the denominator and the numerator are both going to be rational functions. They're both going to be polynomials. As I said in the first section on standard integrals, our end goal is always going to be how can we manipulate the integral we've been given so that it looks like one of our standard integrals on a reference sheet, because then we can just read off the solution. So we're going to go through a few examples, and along the way you'll get to see some handy little tricks that might help you, so you can add them to your toolbox to convert an integral into something that looks like one of the standard integrals and therefore solve the problem. This first example is the integral x squared minus 1 over the integral x squared plus 1 dx. And the first thing I note is how similar the numerator and the denominator are. And in fact, that's going to be our line of attack here. Can I rewrite the numerator so that it looks like the denominator? There might be a little bit left over, but hopefully we'll be able to deal with that. And in fact, you should be able to see that I can rewrite the numerator, x squared minus 1, as x squared plus 1, take away 2. So it is the denominator, but I need to take away 2. And in fact, that's fantastic, because now I can break that fraction up into two pieces. The first piece is x squared plus 1 over x squared plus 1. The second piece being 2 over x squared plus 1. That left-hand side, that left piece, collapses down to something trivial, just collapses down to 1, and that second piece is an inverse tangent. It's a standard integral, so we can solve this problem. So looking for a way to rewrite the numerator in terms of the denominator can often be a very useful strategy, and it's a tool that should probably go in your toolbox. This second example is a little bit more difficult, but the idea is the same. We're going to be able to rewrite that numerator in terms of the denominator and break it up into pieces. One of them will be trivial to solve, and the other one will be a standard integral on our reference sheet. So as you can see, the integral is 4x cubed minus 2x squared plus 1 on the numerator and 2x minus 1 on the denominator. And it shouldn't be too hard to see that I can rewrite that numerator as 2x squared and then in brackets 2x minus 1, and then I've just got a plus 1 left over. So it's what I call a near multiple of the denominator, just as in the first example. And that means I can break this now up into two fractions, and the first fraction just collapses down to 2x squared, and the second fraction now is just 1 over 2x minus 1. This time, that's not an inverse tangent, but if you look at your standard integrals, it shouldn't be hard to see it's in that form for a logarithm. It's the derivative over the function, or a multiple of the derivative over the function. So again, we can solve the problem. In this third example, things are a little bit more challenging, but we're going to learn another tool that we can pop into our toolbox to help us solve the problem. So you can see this is a definite integral now, running between minus 1 and 1. And on the numerator we've got e to the 2x minus 1, and on the bottom, on the denominator, we've got e to the 2x plus 1. And what we can do is multiply everything, every piece, by e to the minus x. And if I do that, I see on the numerator I get e to the x minus e to the negative x, and on the denominator I get e to the x plus e to the minus x. Now that might not look any simpler at the moment, but here's another tool, a really important tool, that's going to go in our toolbox, and we can use this all the time. Look at that denominator, e to the x plus e to the minus x. If we take its derivative, what do we get? We get the numerator. So in fact, this is the derivative over the function. This is a logarithm in disguise. And again, problem solved. So looking for the numerator being the derivative of the denominator, or a multiple of it, is a very powerful tool, and that should go in our toolbox. Now this final example is actually on your reference sheet if you look at it. This is one of the extension 2 integrals, but you should know how to prove it, so that's why we're going to go through it now. So you can see the integral is 1 over the square root of x squared plus a squared dx. It almost looks like one of our inverse trig functions, but not quite. Now this integral requires some sneaky little tricks. We're going to force a common factor, top and bottom. And that common factor is going to be x plus the square root of x squared plus a squared. So I'm going to multiply that top and bottom, and you'll see why in a moment. And you can see what that looks like over there. Now we're going to do something else that's sneaky. See on the bottom there, on the denominator, we've got that square root of x squared plus a squared. We're going to drag that from the denominator, because it's really 1 over the square root of x squared plus a squared. We're going to drag that from the denominator up onto the numerator and rearrange it, as you can see. And then that handy little tool again. Look at the denominator, take its derivative. And again, we get the numerator. So again, this is a logarithm in disguise. And that's how we solve this problem.